Coriolis effect. An object in motion appears to be deflected from its course, as if a force is pulling it sideways. To demonstrate this point, let's imagine a game of catch being played by two people on a merry-go-round that spins like the Earth but is flat. Without rotation, the ball appears to follow a straight path from thrower to catcher. Imagine the ball is tossed from the center to someone at the edge. With rotation, the ball still travels in a straight line in space, but because the catcher is moving, the ball misses. From the vantage point of the catcher, the ball appears to curve away. The direction of apparent motion is to the right when following the path of the ball. Now the ball is thrown the other way. Because the thrower is moving, the ball has a velocity component to the right. The motion of the ball appears deflected to the right, and the ball misses the catcher again. Let's look at a throw across the merry-go-round. Both people move with the merry-go-round. The ball is thrown. Although it flies straight, it appears to be deflected from its original path. Apparent deflection increases as the ball travels farther. In the southern hemisphere, rotation is clockwise when viewed from over the pole. Again, the ball follows a straight course, but its apparent flight path is diverted. This time, the effect is to divert the motion to the left. On Earth, all free-moving objects, including masses of air, are subject to the Coriolis effect. In the northern hemisphere, objects are diverted to the right, as viewed from the direction of original movement. In the southern hemisphere, the deflection is to the left.
In this view of Earth from space, it is clear that the Earth is rotating. However, as an observer on the surface of the Earth, the only indication our planet is rotating is in the observation of the sun during the day and the stars during the night. Every day the sun rises in the east and sets in the west, but we are completely unaware that we are traveling to the east at hundreds of miles per hour. So just how fast are we moving? Well, at the equator, the rotational velocity of the Earth is an incredibly fast 1,018 miles an hour. If you were to travel from the equator to about 30 degrees north latitude, the rotational velocity would have slowed considerably to about 882 miles an hour. Well, why? Well, as you walk north or south from the equator, you're actually getting closer and closer to the Earth's axis of rotation. Because the surface of the Earth is solid, the rotational velocity will decrease as you walk north or south from the equator, because you're actually getting closer and closer to the Earth's axis of rotation. To understand this better, let's imagine that we take the Earth, a sphere, and flatten it out into a rotating disk, like a merry-go-round. If you were to stand on the edge of the merry-go-round, the rotational velocity would be large, and you would feel like you're going to fly off. However, if you stand in the middle, the rotational velocity would be much less, and you would feel like you're barely spinning at all. Now, what if we were to have two people sit on opposite sides of the merry-go-round and try to throw a ball to one another? You can see that as the ball leaves the hands of the person throwing it, it becomes independent of the rotation of the merry-go-round, and therefore follows a straight path. But because the person trying to catch the ball is still rotating with the merry-go-round, they are quickly moved out of the ball's intended path. Because the merry-go-round is spinning counterclockwise, this deflection is to the right. If it were spinning clockwise, the deflection would be to the left. Now, to an observer above the merry-go-round, the path of the ball appears straight. However, to people on the merry-go-round, the path of the ball curves to the right of the intended motion. This experiment demonstrates how the rotation of the merry-go-round appears to cause a deflection in the path of the ball. This also demonstrates how air movement on the Earth's surface can be deflected by the Earth's rotation, a phenomenon called the Coriolis effect. How do we relate the effects of the Coriolis force to air motion in our atmosphere? To answer this question, let's first investigate what would happen to a parcel of air that was initially at rest with respect to the Earth. At 30 degrees north latitude, the parcel is traveling to the east with the Earth. But if we were to shove this parcel at 10 miles an hour to the north, what would happen to its motion? We have already seen from the merry-go-round experiment that the ball would be deflected to the right. But why? The answer lies in understanding something called the conservation of angular momentum. Angular momentum is the product of the mass times the velocity times the radius of a rotating object. The conservation of angular momentum tells us that for a rotating object, the product of its mass, velocity, and radius is constant for that system. Well, what does this mean? Think of a ball swinging around on a string. If you shorten the length of the string, the rotating ball spins faster. Angular momentum, however, is conserved because as you decrease the radius or the length of the string, the velocity or the rotational speed of the ball is increased so that the product of the velocity times the radius times the mass stayed the same. As an example, let's consider a ball that weighs 1 kilogram on a string that is 1.5 meters long, spinning at 5 meters per second. When we calculate the angular momentum, we find its value is 7.5. If we shorten the string, we know that the ball will spin faster. So if the radius of rotation is reduced to 1/2 meter, the rotational velocity must increase to 15 meters per second so that the product of the mass times the velocity and radius remains at 7.5. Now how does all this apply to this parcel that we shove north? Well, as we moved it to the north, the rotational speed of the Earth will decrease. However, because the parcel of air is actually moving closer and closer to the axis of rotation, its rotational velocity must increase by the conservation of angular momentum. If you were standing at 30 degrees north and watching the parcel as it moved, it would appear to be deflected to the right. This apparent deflection is the direct result of the Coriolis force. What is really interesting is that if the parcel continues to be deflected, it would trace out a path along the Earth's surface that kept its original speed of 10 miles an hour constant with respect to the rotation of the Earth. Therefore, the path of the parcel would eventually trace out a circle, much like the path of this baseball on the merry-go-round. Watch as Amanda pushes the ball out to the center, and it makes a complete circle back to her other side. Some important facts about Coriolis force. First, the Coriolis force causes objects to deflect to the right of their intended path in the northern hemisphere, and to the left in the southern hemisphere. This is why low-pressure systems like hurricanes and extratropical cyclones circulate counterclockwise in the northern hemisphere. Second, the Coriolis force affects the direction of an object, not its speed. Third, the strength of the deflection is proportionate to the speed. For example, the faster an airplane flies, the more the pilot must adjust the flight track to account for the Coriolis force. And finally, the Coriolis force is 0 at the equator and maximum at the poles. To leave you with an interesting fact, the effects of the rotation of the Earth are negligible at very small scales. For example, if a pitcher were to throw a pitch at Wrigley Field to home plate at 100 miles an hour, the deflection of the path of the ball is very small, only about 900 microns, which is about 0.9 millimeters, or about the thickness of your fingernail. However, for an intercontinental ballistic missile, if shot a few thousand miles at 1,000 miles per hour, the deflection is hundreds of miles.